Hi everyone, welcome back to the channel. Today I have brought another good problem from rotation chapter, and it's also from Pathfinder book under check your understanding section, question number 25. So there is a figure as you can see on the screen, and the problem states that two identical uniform cones A and B can rotate freely about their fixed central axis, pressing each other uniformly on their entire tapered length as shown in the figure. If the cone A is rotated with a constant angular velocity omega A, it is also shown in the figure. How much angular velocity will the cone B ultimately acquire due to friction between the cones? So obviously in this contact of the cones we have friction. So initially there was angular velocity of A only, but due to friction in final condition or at steady state, B will also have some angular velocity, and we are supposed to find that angular velocity. So one major catch of this question is it's not necessary that at steady state no slipping will occur along this common line. Where both the cones have touched each other. There can be slipping. Still we will call it a steady state. But we are calling it a steady state because the angular velocities gets constant at that time. Sorry, not at that time, but it's get constant at a certain value, which with time will not change. So that's why we are calling that stage as a steady state, not necessarily because there is no slipping between the cones, right? So let's proceed with the solution. I have shown the two cones separately with some separation between them, but it's just for imaginary purpose, for better understanding. But in actual practice there is no such space. It is in contact with each other as shown in the figure, right? So in steady state I have marked the angular velocities as omega A and omega B, and as you can see I have shown the direction of velocities of the points on the common edge of both the cones, and the magnitude of that velocity will also vary because it's a slant face, right? So every point is not at the same distance from the axis of rotation. This point is at a distance of r from the axis of rotation, but this point is on the axis of rotation. This point is something else, not equals to r, right? So all the velocities will be different. So at this far extreme the cone A will have, sorry, not cone A, but the marked point on the cone A will have a velocity of r omega A outward to the plane of the screen, and this vertex, as it is lying on the axis of rotation, it will have zero velocity at that instant. I hope it's clear, right? Let me erase these things. Wait. Sorry. Yeah, it's fine, I guess. Right? So next is similarly I have drawn for B also. Omega B is the angular velocity, and here at this point it will have a velocity of r omega B, and the vertex will have zero linear velocity. So yeah, that's all here. And this is one important line. I have drawn a line like this, right? Something like this. So this line indicates that on this line two points will obviously pass through this line that will be on cone A and B respectively, and I am claiming that these 2 points will have same velocity, right? Because you can see at the left extreme cone A, the point on cone A is having a velocity r omega A, but cone B is having a velocity 0, and this r omega A gets decreased to 0 at the right extreme, whereas for cone B the velocity value changes gradually from 0 to r omega B at the right extreme. So here the velocity increases and here it is decreases from maximum value, and it is increasing from minimum value. So at some point of distance in between these two extremes, there will be a point where VA will be equals to VB, and I have assumed that point only, which I have shown with a vertical line, that where VA will be equals to VB, because they are not at all points VA will be equals to VB. And if this is the VA equals to VB line, at its left points there will be VA greater than VB, and at right side points there will be VA less than VB, as we have shown in the figure. So VA equals to VB obviously implies that omega A into RA equals to omega B into RB. Yeah, let me clarify that I have picked up this length as RA and this much length as RB. Basically RA plus RB is smaller, right? Because these two are in contact. There is no gap. I have already said in real practice. This is just for the better understanding. Anyway, omega A RA equals to omega B RB. So from there we can relate omega B as RA upon RB into omega A. So we will try to find omega B in terms of omega A. So our purpose is to find RA upon RB. Now these two angles, I mean the semi-vertical angles of the cones will be obviously equal as their axes are parallel. So I've assumed this angle as theta and this one also as theta. And from both the cones, using simple trigonometry, we can write from cone A that tan theta equals to RA upon H minus X. I mean concentrate on this triangle. This is, from here you will get tan theta equals to RA upon H minus X. Yeah, I think I have forgot to tell that I have just picked up this length as X from left extreme to the VA equals to VB line, and from VA equals to VB line to right extreme it will be eventually H minus X, because total height of the cone is H given, right? So it's well understood, I guess, from the figure. So as I was saying that from cone A we can write tan theta equals to this, and from cone B we can write from this triangle that tan theta equals to RB upon X. So we'll just equate these two values and we'll get this equation. From here we can get RA upon RB as H minus X upon X, and let's just substitute this here in place of RA upon RB. We will get omega B as H by X minus 1 into omega A. So we're half done with the solution actually, right? I mean, we have manipulated the relation between omega B and omega A, but there is one unknown term in it, right? That is H upon X. So we need to find H upon X. If we can find that, we are done with the question. So for that, we'll take the equilibrium condition of the cone. We can take any cone. I have shown cone B here. It is obviously the cone B. So the cone B at steady state will be obviously in rotational equilibrium as well as in translational equilibrium. But to get the result H by X, we will use the rotational equilibrium condition, because that will give a required result, right? Translational equilibrium is also maintained, but to get H by X term we will involve the torque calculations so that we can involve the distances, right? So I have shown the normal reaction with the blue color. On that slant face, there will be obviously the contact force between two cones, and as all are homogeneous, all the cones, the mass distributions and both the figures are symmetric, you can assume that the distribution of normal reaction is also symmetric, right? So I have assumed here that normal reaction per unit length will be K, some constant, and these distances I have already mentioned, X, H minus X, and this one was the V equals to VB line. So now we'll calculate the torque. Yeah, so let me tell you first one thing, that what are the torques acting on this cone which are keeping it in equilibrium condition, right? So there will be friction torques, two torques of friction in two parts, both will be opposite to each other, and that too will nullify each other, right? As we have already seen that on the left hand side of this line, all the points will have a velocity of VA greater than VB, right? If I am not wrong, yes, VA greater than VB condition was maintained. So you just imagine that this, let's say compare these 2 points, right, on same vertical line. So this point, I mean the point on A, this one is having higher velocity than the corresponding point on cone B. So what will you observe from the frame of A for that particular 2 points? You will see that B point is behind, right? So all I'm saying this just to determine the direction of friction. So on that left part, the friction acting on cone B due to A will be obviously out of the plane. So that I have shown here. And with the similar logic, on the right hand side of this line, VA is less than VB. So you just sit on the frame of A and observe the direction of motion of B and write the direction of friction acting on B opposite to that. You'll get it that the direction of friction will be inward in the plane. So obviously now it's evident that these two parts of the separated by the VA equals to VB line will have torques in two different directions, torque caused by the friction, and that too will be counterbalanced. So let me calculate these torques values. So yeah, I have shown the common edge or the slant face, whatever you can call, and this angle was theta. So let's go at a distance x from the vertex on the axis and then take a differential element of dx, and its corresponding element on the slant height will be something like the slant face will be something like this. So as I've assumed that k is the normal reaction per unit length, and this distance will be obviously dx sec theta, because you can see this triangle. I mean visualizing this triangle, that this length is dx and this length will be dx sec theta on the slant face. So dn, normal reaction on this small differential part, will be k times dx sec theta. So obviously df will be mu times dn, that is mu k sec theta dx, and the torque due to this friction I am writing d tau as df into x tan theta, because it is the distance from the axis, perpendicular distance from the axis of rotation. So this will be d tau, and all these terms are constant, right? Mu k sec theta tan theta. So I've assumed another constant k prime for these terms just for sake of calculation. So tau 1 is basically k prime into integration of 0 to x dx, right? Tau 1 is basically, I am donating, I have written here, right? Tau 1 is basically the torque caused by friction acting on the part left to this line. This line means VA equals to VV line, right? The left part torque is tau 1 and right part torque is tau 2, and these two are opposite in direction. I have shown in figure also. Let me erase a bit so that you can clearly see. Yes, these two are opposite in direction. So for tau 2 the calculation will be exactly similar, just the limit of integration will change. Tau 1 was from 0 to x, right? For this portion the torque was tau 1, and for this portion the torque will be tau 2. So the limit of x for tau 2 will be x to h. So now we'll just equate tau 1 and tau 2, as we have already said that omega b is constant at steady state, so there will be no net torque acting on the cone. Just from they're equating tau 1 and tau 2, we'll get h by x equals to root 2, and that was our purpose, right? To find h by x in some known quantity, so that we can substitute the value of h by x here. If we can substitute the h by x equals to root 2 value here, we're done with the question. So omega b is basically root 2 minus 1 times omega a, and that is the answer for this question, right? So I hope you enjoyed this. I mean, this is one of my personal favorite question from Pathfinder, and it's quite interesting. I guess the first catch was very beautiful, that at steady state it's not necessary to have same velocities that we generally do, right? That if two bodies are in contact at steady state, we just equate these two velocities or point of contacts, and so it's quite a out of box thinking type questions. Next, also the h by x, to find the h by x was also a bit tricky challenge, I would say. So yeah, surely it's not a easy one. I would not say a hard one, because nothing is tough when you once crack the concepts, right? So anyway, I hope you liked it. Thank you all.